So in today's video, we're going to take a look at this very interesting function over here, which is the square root of 1 minus x squared, which I've graphed below over here. You may recognize this as kind of like the semicircle or semi-unit circle function. We're going to actually use this function in order to analyze how the derivative at different points allows us to determine kind of the function behavior and how we can use the derivative in order to determine the equations of tangent lines, which we're going to do in the next video. And so what we're going to do is we're going to actually go ahead and take the derivative of this function first. And we're going to need the chain rule, of course, so I encourage you to review that if you don't remember. If we want to identify our inner function, that's going to be 1 minus x squared, and our outer function is just going to be the square root of x. So if we're going to take the individual components, or the derivatives of the individual components, rather, the derivative of the square root of x, as you may recall, is 1 over 2 square root of x. If you don't remember how I got this result over here, you can just go ahead and review the derivatives of fractional and negative exponents. And then the derivative with respect to x of 1 minus x squared, this is just going to be equal to negative 2x. This comes straight from the power rule. And so what we're going to do now is we're going to use the chain rule in order to kind of combine these together. And if you do that, you'll end up with negative 2x over 2 times the square root of 1 minus x squared. Because we're kind of just inputting this 1 minus x squared right here into x. Or into the square root of x, rather. And we can, of course, simplify this into negative x over the square root of 1 minus x squared. And so this right over here, this function tells us that at any given x value, so if we input an x value, it's going to output the slope of our function, the slope of f, actually, at that given point, or the slope of the tangent line to f at that given point. And so I'm going to arbitrarily change colors for no particular reason. Maybe green is a nice one. And so essentially, what we're going to do is we're going to actually use this equation now to determine the derivative or the slope of the tangent line at different points and see how that corresponds to this function's behavior. So let's go ahead and start off with f prime of 0. That might be an interesting point to take a look at. And if we input 0 into this function, we're going to end up with negative 0 over the square root of 1 minus 0 squared, which is just going to be equal to 0, of course. And so this tells us that at this point, at x equals 0, the slope of our tangent line is 0. It means that we have a horizontal tangent line, right? Because if the slope of a line is 0, then it means that our line is just going to be a horizontal function. And so if we were to identify that point, this is the point right over here where x would be equal to 0. And it looks to me, and I mean, if we were to even just approximate the tangent line, it would, of course, be vertical, right? Or rather horizontal, because, we're not really increasing or decreasing at this instant. The instantaneous rate of change is 0 because we're not increasing, but we're not decreasing either. Like at this moment, our slope is equal to 0. The slope of our tangent line is equal to 0. Now, what about f prime of negative 1? Well, in this case, if we were to input negative 1 into our function, then we would end up with positive 1 over the square root of 1 minus, essentially, negative 1 squared, which is just 1. And that's going to be equal to 1 over the square root of 0, which is 0. And so this right over here, this is kind of an interesting result, so we're not really going to accept this answer over here. We're going to say that the slope of our function, or the slope of our tangent line, this is just going to be undefined, right? This is undefined. And so it seems as though if we were to think about, the graph of f prime of x, then we would have an asymptote at this point. We would have a vertical asymptote. And so what this tells us, if we were to look graphically, this tells us that we have what we would say a vertical tangent line. And if we were even to look at it kind of graphically and approximate the tangent line x equals negative 1, it seems like the best approximation would be this vertical line right over here. It would be a vertical tangent line because, the equation of this tangent line would be x equals something, right? This would be x equals some value. It would be a constant function. And so the point is that the slope of our tangent line is undefined at this point, and if we were to think graphically, it would correspond to a vertical asymptote on the graph of f prime of x, and so that tells us that we have a vertical tangent line. And we can do the same thing for f prime of 1, of positive 1, and this will be 1 over the square root, or actually this will be negative 1 over the square root of 1 minus 1, which is just negative 1 over 1. Or actually negative 1 over 0. And so this, of course, is just going to be equal to, or this is just going to be undefined as well. And if we were to look at x equals positive 1 on our graph, it also looks as though we have a that's not right. Okay. It looks as though we also have a vertical tangent line at this point. So essentially, whenever f prime of x is equal to 0, then this right over here tells us that we have a horizontal tangent line. So a horizontal tangent. And whenever f prime of x is undefined because of kind of an asymptote on the graph of f prime of x, over here in these two cases as we saw, then here we'll have a vertical tangent. So a vertical tangent line because our slope is undefined, and the reason for it being undefined is because we have a vertical asymptote on f prime of x at these given values. And in general, I encourage you to actually take the derivatives, or actually evaluate the derivative at different points over here and see how that corresponds to the function's behavior. Because if you look at this point, for example, here we're increasing, and that would correspond to a positive derivative. And then if you look at this point, for example, here we're decreasing, and that would correspond to a negative derivative. So I encourage you to kind of try it out with this function. This is a pretty interesting function to look at because it's kind of like the semicircle function. And kind of try it out and see how we can actually understand how this function behaves using the derivative.